Last month, many media science outlets were filled with headlines of 6 new Exomoon candidates announced by a pair of astronomers from the University of Western Ontario. If true, then this would be a major result for astronomy. An exomoon is simply a moon around a planet which orbits a star other than the Sun, in other words, one many light years away. But unlike exoplanets, they have been persistently elusive. Up to now, there's only really been one compelling exomoon candidate in the literature, so the announcement of 6 new candidates represents a major haul. But science is an act of skeptical interrogation, and so today I'm going to share with you an exclusive look at an independent reanalysis of this claim from the Cool Worlds lab. So stay tuned as we uncover the truth behind the headlines. Exomoons, beguiling worlds that have eluded astronomers since the dawn of the exoplanet era. We know that they must be out there. Moons are so abundant in the solar system that it would be truly bizarre for them to not exist elsewhere in the cosmos. Saturn alone has 82. Yet, the challenge with exomoons is that even our most successful planet hunting methods can only find worlds about the same size and mass as that of the Earth, and not much smaller. In contrast, the largest moon in the solar system, Ganymede, is 40 times lighter than this. Because of this, there has always been an expectation that most exomoons are likely too small for us to detect, at least for now. Nevertheless, perhaps there are instances when supersized moons form in these alien systems, and thus we could detect them. After all, the discoveries from exoplanets have taught us that there are extreme, bizarre, unusual systems out there which have very little resemblance to that of our own. A good example of this is a Jupiter-like exoplanet called Kepler 1625b, which shows evidence for a Neptune-sized moon around it. That system made the headlines in 2018 after my team used the Hubble Space Telescope to detect 2 clear and consistent signatures of a large moon. To date, this remains the only case where we have 2 independent lines of evidence indicating the existence of an exomoon, and so on that basis I personally feel comfortable referring to it as an exomoon candidate. Now, the reality of this exomoon candidate remains unresolved, and that really deserves a separate video for another day. But suffice to say for now that this candidate remains an exciting possibility. Certainly there are other exomoon possibilities in the literature. For example, in 2014, a team led by David Bennett announced a gravitational microlensing signal that could either be caused by a free-floating planet with an exomoon, or a low-mass star with a planet. But it just wasn't possible to clearly distinguish between them. A case of frustrating ambiguity. Is this an exomoon candidate then? Well, there doesn't really exist a consensus about how to define what an exomoon candidate is. Are 2 lines of evidence needed? Does it matter if the signal in question is known to be highly ambiguous with more mundane explanations? Lower the bar enough and every exoplanet could be legitimately considered an exomoon candidate. After all, we cannot totally rule out the existence of small moons for any exoplanet. The debate about what constitutes an exomoon candidate, or indeed an exoplanet candidate, or even a black hole candidate, is a sticky one. In the Cool Worlds lab, we've seen enough ghosts in the machine after years of looking that generally we don't get out of bed unless we see 2 pieces of evidence indicating an exomoon. Fool me once, shame on you. Fool me twice, shame on me. But to be clear, that's just our working protocol. It's not intended as some kind of formalized definition for the rest of the astronomical community. Right now, when it comes to really any kind of astronomical detection, it's truly a wild west out there about how one defines what a candidate truly is. With this history in mind, let's get into the recent claim of 6 new exomoon candidates led by Chris Fox and Paul Wiegert from the University of Western Ontario. So when I first saw this paper's title, my immediate reaction was one of excitement and curiosity, like seeing a trailer for some epic new Hollywood film. Why? Well, for years now, my recently graduated student Alex Tichy and I have been saying that this is exactly what we need. Let me explain that. The field of exomoons is undeniably niche. It doesn't feature as a key role in any organizational roadmap, such as that of NASA. There's literally a handful of us on the entire planet trying to make this happen. I know that to Alex and I at least, this is truly bizarre. We do not understand why more people in the astronomical community are not incredibly excited about the opportunity that exomoons represent. New worlds calling out to us, promising diverse, startling, and surely breathtaking discoveries. So in my team, we've come to the realization that the success of the field depends upon building a community. It can't just be us. There needs to be dozens of exomoon research teams fostering a competitive yet collegial field. And so, seeing a new team enter the fray was truly wonderful to see. At the same time, the claim of a new exomoon is a big deal, let alone 6. And so this demands a certain degree of community skepticism. It's important to realize that this is baked into the very way in which science operates. Science, at its core, needs to be reproducible. If I claim that a certain drug cures a disease, another lab working in another part of the world should be able to apply that same drug to the same disease and observe the same outcome. And yes, there will surely be statistical fluctuations, and occasionally some teams might disagree, but the basic result that this drug is effective should be agreed upon by the majority of independent studies. That reproducibility, that community skepticism is intrinsic to how science works.
Science is more than a body of knowledge. It's a way of thinking, a way of skeptically interrogating the universe with a fine understanding of human fallibility. If we are not able to ask skeptical questions, to interrogate those who tell us that something is true, to be skeptical of those in authority, then we're up for grabs.
The demand for reproducibility sounds like a simple one, but applying that simple rule when assessing the credence of various scientific claims is very powerful. In the case of Kepler 1625, recall there were 2 pieces of evidence that we argued for to suggest an exomoon, and a second team independently came along and recovered both of those pieces of evidence. In a third study, a new team, they recovered one of the 2 pieces of evidence. So for Kepler 1625, there is not universal agreement, but 5/6 of the time these studies are agreeing with each other. And on that basis, I would say it's fair to call this an exciting possibility still. The 6 new exomoon candidates that were just recently announced, they come from an analysis of NASA's Kepler telescope data. But for each of these 6, only 1 line of evidence is proposed for their existence, not 2. Although my team wouldn't use the same criteria, largely because we've frankly been burnt too many times before, there's nothing fundamentally wrong with that, and the possibility of 6 new exomoons is very exciting. The line of evidence used to argue for these 6 new exomoon candidates comes from a technique called transit timing variations, or TTV. And that was actually the first method that was seriously proposed as a means of detecting exomoons back in 1999. And indeed, I actually devoted much of my own PhD thesis from 2007 to 2011 to studying and understanding this technique. To describe it in a nutshell, a moon's gravity should tug on the parent planet, causing it to wobble around in its orbit, and this gives rise to slight changes in the time it takes for the planet to complete one full orbit of its star. Now we can time exactly how long these orbits take by measuring the eclipses or transit of planets in front of their stars. Indeed, that's really what the NASA Kepler mission was all about. The TTV method is a very powerful way to look for exomoons, but it also has some major drawbacks. For one, the amount by which the planet wobbles as a result of the moon's gravity depends on how heavy the moon is, multiplied by the separation between the planet and the moon, just like the law of pivots. And so what that means is that when you see a wobbling planet, you can't really tell how heavy the moon is. You only get the moon mass multiplied by the separation. Second, and most critically, we see TTVs all the time. They're very common, but they're almost always caused by planets jerking other planets around, not moons. So just seeing a TTV alone is rather ambiguous. Indeed, for all 6 of these exomoons, the University of Western Ontario astronomers note that a hidden planet could also be equally responsible. With all that said, the most basic claim here is that these 6 exoplanets exhibit moon-like TTVs, and so that claim really serves as the focus of my new paper, which I'm happy to say has just been accepted for publication. To check the claim then, I break it down by just asking 3 simple questions about each planet. Question 1. Do these exoplanets show some evidence for TTVs of any kind? Question 2. Do they show evidence for a periodic TTV? In other words, a repeating signal that we would expect moons to cause. And finally, question 3. If you fit a full exomoon model to the data, does it find that the moon has a mass greater than 0? Really, one should expect a true exomoon to give a yes to all 3 of these questions. Now, I have to say that working on this paper was kind of hard, because I kept thinking about how great it would be if one or more of these exomoon candidates passed the tests. It would mean that we would have new exomoon candidates to work on in the future, incredibly exciting objects. And indeed, the entire field of exomoons would surely benefit from having more positive candidates in the literature. And frankly, my own career, my fate is somehow intertwined with that of exomoons at this point. But science is a cold mistress. Its results often stare you very plainly in the face. It doesn't care about what you think or what you want or how you feel. It just is. And so, as you can probably guess, after running these tests on these exomoon candidates, I find that none of them passed the tests. You can see here a little summary chart of this, where the rows give the names of the 6 planets in question, and the columns list the 3 questions that I posed. I also added Kepler 1625b for comparison, although unfortunately the limited data there doesn't allow one to test question 2 for subtle reasons discussed in the paper. For 2 of the planets, KOI 268.01 and 3220.01, they don't pass any of the tests, not even one. For KOIs 303.01, 1888.01, and 1925.01, just a single test is passed for each. KOI 1925.01 also shows strong evidence for a rather elliptical orbit too, which would make moons rather difficult to retain. This leaves us just with KOI 2728.01, which passes 2 of the 3 tests. However, it fails the test for a periodic TTV, so let's look at that one more closely. Exomoons are expected to cause sinusoidal TTVs, so that really means a very kind of simple wave-like pattern to the data. And the period of that TTV is governed by the period of the moon around the planet. And that value really shouldn't be changing over the timescale of a few years. It would take millions of years for the orbit of a satellite to appreciably change. Okay, so if we fit a simple sinusoid to the data, it seems to do a reasonable job here, but the data is sufficiently noisy, as you can see from the error bars, that it's hard to tell if this sinusoid is real or just a figment of the noise. Now, one could imagine testing this by building a new Kepler telescope, sending it out into space, and measuring more TTVs for this exoplanet. If so, we would expect that we could propagate this sinusoid forward in time, and the new TTV should line up. In fact, that sinusoid should match the future data better than just a flat line predicted if no moon were present. Testing claims through future observations and experiment is the very core of how science operates, as Feynman once famously encapsulated.
If it disagrees with experiment, it's wrong. And that simple statement is the key to science. It doesn't make a difference how beautiful your guess is, it doesn't make a difference how smart you are who made the guess, or what his name is. If it disagrees with experiment, it's wrong.
Testing hypotheses with new data is great, but the idea of building a new Kepler space telescope just to test this one hypothesis is an expensive proposition. This is where an idea called cross-validation is going to come to the rescue. Instead of collecting some more data, let's just imagine that we only have the first 80% of the existing data to work with, so we hold back the last 20%. So in a way, you can imagine that 20% being like new observations taken in the future by another telescope. We then fit our models to the 80% in hand, often called the training set, and we ask, how good are the fitted model's predictions versus a simple flat line when applied to the holdout set? If the moon is real, then we should expect it to give a better prediction than the simple flat line. In fact, we don't have to just chop off the last 20%, it could be the first 20% or the middle 20% or indeed any other random 20% of the data. So in cross-validation, we do this experiment thousands of times, changing the 20% segment in each one of the experiments. And we count up how often does the moon model outperform the predictions of the flat line model. It should also be noted that this is a very common strategy in machine learning, in particular when training deep neural networks. Sadly here, we find that the flatline model outperforms the moon model at a ratio of almost 3-to-1. So what the deuce is going on here? We have a planet who passes the test for having TTVs, but fails the test for having periodic TTVs. How does that make sense? Well, it's difficult to say for sure, but one possibility is that there are indeed TTVs for this system, but they are quasi-periodic in nature, going up and down almost like random excursions, and that could be caused by the bubbling, frothing active stellar surface. And indeed, there is precedent for seeing exactly this. As an example, in 2011, Jean-Michel Desire discovered the hot Jupiter exoplanet Kepler-17b orbiting an active star and noticed strong evidence for TTVs. However, when they plotted the strength of this TTV signal versus the period, they found that the supposed TTVs occur at nearly exactly 1/2 of the stellar rotation period. That kind of coincidence is immediately suspicious, and further studies show that the TTVs were indeed spurious, illusions caused by the star rather than genuine gravitational interactions. A neat way to visualize this is that the signal power represented by the light regions in this spectrogram seem to come and go over time. They don't persist as we would expect for a real signal. So if I take that cross-validation framework that I described before and now apply it to this well-known case of spurious TTVs caused by stellar activity, I end up getting a similar result. Specifically, the flat line model outperforms the periodic TTV model at a ratio of almost 2-to-1. In other words, the periodic model is not making very good predictions. And so I think that's naturally explained by stellar activity and could be a very reasonable explanation for what is going on with KOI 2728.01. Now I have to say it's certainly disappointing that these 6 claimed exomoon signals do not appear legitimate, although of course there could still be small, undetectable moons around these worlds. In my paper, I'm even able to place upper limits on how small those moons would have to be to have evaded detection thus far. And although this is disappointing, hey, look, we've been here before. Back in 2014, my team showed that another possible exomoon, Kepler 90G, was also likely bogus. And it's not just exomoons, indeed exoplanets has also suffered a similar history. Be it the 1855 claim of Captain William S. Jacob, which I recommend you check out our video about, or Peter van der Kamp's white whale of Barnard Star, or the famous Alpha Centauri exoplanet just a few years ago. Exoplanet claims do not always withstand independent scrutiny either. But I want to be clear here that nothing is broken. This is how science is supposed to happen. Claims should be skeptically interrogated, and invariably some of those claims will not withstand said scrutiny. The ability of science to challenge its claims, to skeptically stress them to various observational tests, is exactly its strength. It's not dogmatic. Everything is up for grabs. Only by challenging its claims, even sometimes foundational ones, does science enable continuous advancement and learning. Step by step, we'll get there. Exomoons will reveal themselves. Yes, maybe not this time, but I promise you that we will find them through a lot of care, diligence, hard work, and yes, a healthy dose of skepticism. Thanks for watching, everybody. I'd like to give a special thank you to our new supporters, Doug Daughaday, Andrew Jones, Jason Allen, Mark Lejau, Alina West, and Tristan Zajong. You guys are awesome. Thank you so much for your support. If you liked this video, then do please consider subscribing to our channel. And until next time, stay thoughtful and stay curious.